Hello, can everyone hear me?
So good morning, everyone. Welcome to the morning session. And our first speaker is Hazel from Macquarie University, who will tell us about stone type dualities from categorical first principle. Please.
Thank you. And thank you to all the organizers for allowing me to speak as well. I will, first of all, say that this topic has been discussed yesterday, so the background, and so I'm sorry if it's boring for some. I will also say that the first half of this talk is based on my master's work under the supervision of Richard Garner, and the second half is my current work, also under Richard Garner and Ross Straight, and I'd like to thank them as well. Okay, so let's get started. First of all, classical stone duality, an equivalence of categories between the opposite of Boolean algebras and the category of stone spaces, also known as Boolean spaces, or totally disconnected compact Hausdorff spaces. So compact Hausdorff spaces with an extra separation condition. Now, this was proved in the 1930s by Stone and was one of the first equivalences of categories that was genuinely kind of non-trivial. And for that reason, it might be surprising that there hasn't really been a very nice, clean kind of categorical proof of it. Clean and illuminating, if you like. So one of the formulations that does exist is using dualizing objects. Here, a Boolean algebra B is sent to its Hom set endowed with operations, and those the pre-image of the maps into two correspond to ultrafilters on B. And then in the other direction, we Hom into the discrete space with the two element set as its underlying set. Now, we might wonder what can we do to try and formulate this in a nice way, and something that might seem kind of related, but not necessarily expected to be totally related, is the ultrafilter monad, which is well known as the codensity monad for the inclusion of finite sets into sets. Now, first of all, I'm just going to give you, if you haven't seen ultrafilters before, really, you're not really familiar with them, then I'm not going to give you a formal definition because it won't sink in this short of time. But basically, they're upwardly closed, so kind of maximal in the Boolean algebra, a maximal proper subset, and I've got my diagram there. Okay, so the ultrafilter monad can also be given as the composition of this adjunction. So here, in one direction, we have a set going to its set of subsets, i.e. the power set as a Boolean algebra. And in the other direction, we have just the set of ultrafilters on that Boolean algebra. And I've just written here the unit and co-unit, very straightforward. Now, the monad itself, it sends a set to its set of ultrafilters, just the composition of those two, obviously. And this can be regarded as sending a set regarded as a discrete space to its stone check compactification. Now, in the late 60s, Monez proved the result that the algebras for the ultrafilter monad are in fact compact Hausdorff spaces, thereby making it clear that they are algebras in the universal sense, albeit with operations of infinite parity. And this also might seem a little bit surprising. I feel like there's a few things that might seem a bit surprising in this talk, and I hope you, as my listeners, will find it interesting because of these little surprises. So I will give a very brief kind of overview of how this can be, this result can be seen. It requires two salient facts here. One is that ultrafilter convergence is a description that can completely determine topological space. As in, you can give a topological space in terms of open sets or ultrafilter convergence, and that is a perfectly reasonable description of a topological space. The second, sorry, that shouldn't have been coming through. The second fact is that compact Hausdorff spaces are particularly nice with respect to ultrafilter convergence, because compact spaces have at least one point of convergence, and Hausdorff spaces have at most one point of convergence, which means you have a function from the set of ultrafilters to a space. So then, let me come back to what I was saying about, we might wonder how we can extract stone duality in some nice way from something that seems slightly unrelated, as in the ultrafilter monad. And here I've depicted the comparison functor, and this sends a Boolean algebra to the algebra of Clopin subsets that is formed by using that Boolean algebra as the Clopin subsets. Sorry, I should restate that. You take the Boolean algebra and the elements of the ultrafilters. Sorry, haven't had a lot of sleep lately. We take the algebra of Clopin subsets anyway. Okay, so on the right we have the free and forgetful functors, and as I kind of alluded to earlier, the free functor is the stone check compactification of the set regarded as a discrete space. Now, de Book's adjoint triangle theorem tells us that K has a left adjoint, and in fact we have this result that the left adjoint is quite explicitly given as this equalizer in the category of Boolean algebras. And this does send, I'm mixing things up, mixing my words up. This does send a space to the algebra of its Clopin subsets. Okay, so firstly we have that the co-unit for this KL adjunction is invertible, and thus we can say that that the comparison functor is full and faithful. Now, it seems like it would be a little too nice if the essential image of the comparison functor was the category of stone spaces, but that does indeed end up occurring. So it turns out that the unit for this junction is invertible precisely at the category, at objects which are stone spaces. And this is a really clean and nice kind of categorical account of stone spaces. And we can therefore say that the essential image of the comparison functor for the ultrafilter monad is therefore the category of stone spaces. And so we have that this adjunction restricts to classical stone duality, which is what we wanted. So we might ask how we can extend this result and use it, in other stone type dualities. There are many generalizations of stone duality that have been done over the years. We saw one yesterday in Marco Aberdini's talk with Priestley spaces. And in fact, this machinery does work in that case. And I showed this also in my master's work. I'm not going to go into very much detail here because I'm not going to have time, but I can say that using the prime filter monad, we can extract Priestley spaces in the same way. And I will also note that the category of algebras poset to the beta here, beta hat, is in fact the compact ordered spaces introduced by Nachman that Marco Aberdini discussed yesterday. So what else could we do with this machinery? As I said, there are many generalizations of stone duality. And one thing that has been worked on more recently than Priestley in the 70s, or Stone's original result, is that of Skewballing Algebras. And I imagine not many people are going to have any familiarity with those. So I will give a bit of an overview, and I will first tell you what the result is. So this can be considered a non-commutative stone duality, and this was shown by Kudrai Siva. I really hope I'm pronouncing that correctly, in 2012. And she showed that left skew Boolean algebras with the P refers to proper maps. Don't worry too much about that. And the category of sheaves over locally compact stone spaces. And the maps here, the morphisms in the sheaves over locally compact stone spaces aren't what you might think, but I will get to that. Okay, so I'm going to tell you a bit about skew Boolean algebras, as I said. So left skew Boolean algebras in particular here, we have non-commutative binary operations, meet and join, a nullary operation 0, which acts as a normal bottom element in a lattice, and a binary operation called difference. And these might seem like not very illuminating, but I will give some examples, and hopefully they'll become a little bit more clear. So the first example I'm going to give is in some sense kind of the canonical example. So take a set A and B, and take par AB to be the set of all partial functions from A to B. So given two partial functions in par AB, F and G, we can define our operations as follows. F meet G is given by the restriction of the domain to the intersection of the two functions, and then taking just the left one. And this is the left part of the skew description. We have override. Hopefully this is all clear from my pictures. I think they basically tell everything here. Difference, and the empty function is our 0. So now I'm going to also introduce another example. So I discussed earlier the two-element set being this kind of special thing in stone duality, or rather, objects with an underlying set being the two-element set have kind of a special role in classical stone duality. This is also the case in Priestley duality, I'll note. this is what I chose as an example for that reason. So 3L is the Skewballing algebra that has two non-zero elements. Here I've labeled them 1A and 1B, and they have operations that are given by the equations I've given on the right. And we can take what's called a D quotient. This comes from semigroup theory. And we can take the ones, which are in what's called a D class, and the zero is always in its own D class, and we quotient by the non-commutative kind of stuff going on, and we get the two-element Boolean algebra, which of course is a Skewballing algebra, just a sort of degenerate case. Okay, so now I'm going to talk about something that seems really quite surprising, I suppose. Seems completely unrelated to Skewballing algebras, and that's the category of polynomial functors on set. Now I'm going to give you a description, like you might be familiar with this category, but the presentation that I'm giving might not be that familiar. So I'll go over it here. So we can describe the objects as functions. So P and Q, and then a morphism is a pair of functions f and g such that this diagram commutes, and therefore these morphisms aren't these morphisms are a pair of functions between any pair of objects. Okay, so we have an adjunction from poly to left skew Boolean algebras, and here we can think of poly as taking the place of set in the ultrafilter monad, and we have in one direction the left adjoint is induced by homming into this 1 down to 2, which just picks out true, and an object is sent to the partial sections on the power set of the base, and these can also be written as I've written them down the bottom. Okay, so the ultra-sheaf monad was introduced by Kennison in 1981, and this takes a polynomial functor here to, at the bottom, it's just the Stone-Check compactification that we saw before, beta, and the top element, the top is given by the fibers are given by the push forward of the unit of the ultrafilter monad, and it turns out that the fiber over an ultrafilter is actually an ultra product, which is really quite interesting and nice, and very unexpected in my opinion. Okay, so here we have this theorem by Kennison that the algebras for the ultrasheaf monad are sheaves over compact Hausdorff spaces, and in fact we can now say that the morphisms that we saw in poly are what the morphisms look like here, rather than the ones that you might think. Okay, so we can ask, is the comparison functor full and faithful here as well? And it seems like it's probably not, which is sad. So coming back to Kudryat-Siever's result, we have sheaves over locally compact stone spaces, which is not really what you would want. Here, for it to be truly what we want, we would want sheaves over stone spaces, which is a result that comes out of this, but only if you restrict on the category of less skew Boolean algebras to objects whose D-quotient is actually a Boolean algebra. And that's not the case for all of them. Some of them are generalized Boolean algebras if you're familiar with those, but if not, don't worry about it. So currently I'm working on what can we get? Like, we need to restrict on both sides to get the duality with sheaves over stone spaces. But what else can we do with this adjunction? And that's basically my my current project. And so basically this will restrict to in the normal just image of the comparison, essential image of the comparison functor. Don't know. Don't really know yet. So thank you for listening, and sorry I went a little bit over time.
So thank you for your talk. Now we have some time for 2 questions at most. So first I ask in the room if there is anyone who would like to ask a question.
Hi, thanks for the talk. It was really interesting seeing stone duality from this new perspective. I agree with you when you say that it's quite surprising that you get sheaves coming out at the end of it. So my question is quite open-ended. I wanted to know whether you could give any intuition for why we might see sheaves there.
I think that one of the main things that you can think about is that discrete sheaves are just, you know, index sets. So I think once you kind of think about that and then apply the stone check compactification kind of process, then it becomes more obvious. But saying that, this is very much, yeah, work in progress. So that's really all I can say at this point. Does that help?
Thank you. There's another question from.
Hello. So I just wanted to know whether this work has a connection with the PhD thesis of Sam van Gogh, which was on this topic, if I remember correctly.
Absolutely. So this is very much related to Sam van Gogh's thesis. So I'm trying to remember, I believe it was, he also extended this to skew, I believe he extended this to skew lattices, skew distributive lattices. And this is actually where we'll be looking at next, and therefore potentially sheaves over local Priestley spaces is the result. That's from a paper by Mai Gurka, Sam van Gogh, Andre Bauer, and some other people. Sorry, I can't remember exactly who, but yes, absolutely, this is related. And in this case, we'll be taking, partially ordered sets as our, like we'll be looking at some kind of category of polynomial functors on the category of partially ordered sets in a completely analogous way to how this is working for stone duality. So so extending it to Priestley duality and Priestley type duality for skew lattices. Thank you.
So thank you very much. I think we have to stop the discussion here to be on time. Thank you again for your talk, Ellie.
Thank you.
We have 2 minutes break for the next talk.